Welcome to this video on pyrophoric carbonization, focusing on the long-term, low-temperature ignition of wood. We will cover carbonization, electrical leakage, and fire cause analysis, aligning with NFPA 921. The purpose of this video, aligned with NFPA 921, is to apply the scientific method, examine carbonization, evaluate electrical leakage, and use defensible terminology in fire investigations. The scientific method framework involves 6 critical steps: identifying the problem, collecting and analyzing data, developing and testing hypotheses, and selecting the final hypothesis. All conclusions must follow this process. Problem identification begins with an unexpected fire, lacking an open flame source. This often involves evidence of prolonged heating, leading to a delayed ignition timeline. Data collection requires scene examination, inspecting electrical components, assessing material condition, and gathering witness information to build a comprehensive case. Data analysis involves reviewing heat exposure history, examining material transformation, and tracing electrical pathways to identify faults and potential ignition sources. Hypothesis development considers long-term heating, leading to carbonization. This creates conductive char, allowing for electrical leakage and potential smoldering ignition. Hypothesis testing involves comparing alternative explanations, eliminating those inconsistent with the data, and assessing the probability of remaining hypotheses. Key terminology includes pyrolysis, which is chemical decomposition by heat, carbonization, the transformation into char, smoldering ignition, and self-heating, which is internal heat generation. Short-term ignition temperatures occur around 250 degrees Celsius. However, ignition is not a fixed threshold and varies widely based on material, duration, and environmental factors. Long-term low-temperature ignition occurs below 250 degrees Celsius. It requires prolonged exposure over time and typically results in smoldering combustion. Wood is a dynamic material. Prolonged heating causes moisture loss, structural cracking, and changes in permeability, affecting how heat and gases travel. Carbonization is the process of wood turning into carbon-rich char. Char formation reduces ignition resistance and increases the material's chemical reactivity. Char exhibits conductive behavior, allowing current flow. This creates leakage current pathways and presents a significant resistive heating risk. Electrical leakage acts as a heat source, involving low current flow that causes localized heating. This process is often undetected without specialized inspection. Standard protection devices have limitations. The current may be below trip thresholds, and protection devices may not detect series arcing or current flowing through carbonized paths. The smoldering ignition process begins with carbonization, followed by oxygen diffusion into the porous char. Exothermic reactions then lead to self-heating oxidation and potential ignition. Carbonization rank relates to char reactivity. Wood char is highly reactive, leading to lower ignition resistance, meaning less energy is required for combustion. The term pyrophoric carbon is controversial in fire investigation. The underlying mechanism involves a complex, continuous evolution of physical and chemical changes. Field indicators for this mechanism include deep charring, proximity to electrical sources, and evidence of a delayed, long-duration, low-temperature heating timeline before ignition. Legal considerations. First, reliable methodology is critical. NFPA 921 requires use of the scientific method. Courts accept conclusions when investigators properly follow the scientific method. Opinions fail when steps are skipped or assumptions replace analysis. Second, the science applied must be relevant to the facts of the case. In long-term heating scenarios, relevant science includes carbonization of wood, increased conductivity of char, leakage current heating, and smoldering ignition. Finally, clear terminology matters. Courts have rejected vague or misleading terms, particularly when not clearly defined. In short, when NFPA 921 methodology is followed, relevant fire science is applied, and precise language is used, delayed ignition opinions are scientifically and legally defensible. A common mistake is treating ignition as an instantaneous event. NFPA 921 recognizes that time is a critical variable. Long-term, low-level heating can progressively alter materials through drying and carbonization, significantly reducing ignition resistance. Ignoring exposure duration leads to incomplete or incorrect conclusions. Another pitfall is relying solely on published ignition temperatures. Those values apply to short-term exposure and do not account for prolonged heating. Fire science demonstrates that materials can ignite at much lower temperatures when exposed over extended periods, typically through smoldering ignition rather than flaming. Using vague or imprecise terminology undermines credibility. Courts and NFPA 921 emphasize describing observable processes, such as carbonization, self-heating, and smoldering, rather than relying on controversial or poorly defined terms. Clear language strengthens both scientific and legal defensibility. NFPA 921 requires the use of the scientific method in all fire investigations. Investigators should identify the problem, collect and analyze data, develop multiple hypotheses, and test those hypotheses against the evidence. This disciplined approach is essential in delayed ignition cases where assumptions can easily replace analysis. Prolonged heating can significantly alter materials. Investigators should carefully document color changes, depth of charring, texture, cracking, and transitions from wood to char. These physical changes provide critical evidence of carbonization and long-term heat exposure. Investigators must assess not only temperature, but also duration of exposure. Low-level heat applied over long periods can reduce ignition resistance and lead to smoldering ignition. Evaluating cumulative heat effects is essential to understanding delayed fire development. Long-term, low-temperature ignition is a documented fire science phenomenon. While terminology such as pyrophoric carbon has been debated, the underlying processes, carbonization, self-heating, and smoldering ignition, are well supported in the literature and recognized within NFPA 921 when properly described. Prolonged heat exposure fundamentally alters material properties. As wood carbonizes, its ignition resistance decreases and its reactivity increases. These changes allow ignition to occur at temperatures far below those associated with short-term heating. Carbonized materials can conduct electricity. Leakage currents tracking across these paths can produce localized heating sufficient to sustain smoldering and lead to delayed ignition, even when protective devices do not operate. Remember the importance of the scientific method in all your analyses.